Hi, my name is Alexandra Higley, and this summer I worked with West Virginia University's Department of Physics and Astronomy, as well as the North American Nanohertz Observatory for Gravitational Waves, which is a collaboration that is looking for gravitational waves in pulsars, and pulsar timing arrays. And that's quite a mouthful. And you might be wondering, what even is a pulsar? And to put it as simply as possible, a pulsar was once a massive star that have since shed out all their outer layers in a supernova explosion, leaving only a small, dense, rapidly rotating, and highly magnetized object. Additionally, these pulsars have radio beams that come off of either end of their magnetic poles. And the way that you can visualize this is you can think about a lighthouse. And you can imagine that if you're standing in front of a lighthouse, every single time that it rotates, you're going to be hit by a beam of light, right? Pulsars are essentially doing the same thing with Earth, where every single time they rotate, a beam of radio frequency is coming towards us and interacting with us. And every single time that one of these beams hits us, we will receive a pulse from this pulsar. And since pulsars rotate so fast and their rotational period is so steady, these pulses, we can predict when they come to the millisecond, which makes them essentially clocks in space in a way. And with this array of clocks in space, we can look for gravitational waves. However, many factors go into predicting the time of arrival for each pulse, such as modeling the interstellar medium, figuring out where we are in the galaxy, where we are in our own solar system. And the one that we looked at this summer is the position of the observatory that is looking at the pulses, right? And what we supposed was if there were some sort of small error in the observatory position, how might that look like after gravitational wave analysis? Would the observatory position cause some sort of noise that might overpower gravitational wave detection, or worse, look like a gravitational wave? So basically what we did was we wrote a program that incrementally increased the observatory position. We started at 0 meters, went to 1 meter, 10 meters, 100, etc. And for each new increment, a model was created, which we would run through our Tempo 2 program, which is a pulsar timing software. And the software would give us physical parameters for the pulsar, as well as the RMS, which is the root mean squared, which is essentially an error. And we could see how these parameters changed as we increased the observatory position offset. So this composite plot of these parameters is that of a normal looking pulsar, which is what the vast majority of the pulsars looked like after we ran it through our process, which is pretty much only at extreme distances do you see any sort of major difference in any of these parameters, which is good. We don't really want to see much of a difference in anything if the observatory was offset by only like a meter or so. That would be bad. However, even though most of the pulsars looked good, there were a handful, very small amount of outliers that were just insane, crazy, that had a big offset for no reason. We're not really sure why these pulsars were the way that they were. However, we did plot them against the regular pulsars. The regular pulsars in this plot is shown in light blue, and the outliers are shown in these colored stars. And this is just a plot of the sky, right? And as you can see, all of the outliers seem to be in the same region of the sky. So we think that they might be spatially correlated, but we're still looking into it. Also, over here we have some images from Sloan Digital Sky Survey, which show where in the night sky two specific pulsars are. These first two are the same pulsar. And basically what you're seeing here is a white dot and a red dot. The white dot is where the pulsar starts out when there's 0 offset in observatory position, and the red dot is where the pulsar ends up after an offset of 100,000 meters, which is large. So here they're on top of each other, no difference. But if you zoom in a bit, you can see that there is a difference. It's just very minute, but even this minute kind of difference might be significant for gravitational wave analysis and detection. Here is our same outlier. This one is here. And there's a bigger offset, more significant. Again, we don't know why. We're looking into the outliers, and that's part of our future work. However, in conclusion, for the most part, we see that at only at large distances, distance offsets, is there like a sizable difference in physical parameters such as right ascension, declination, proper motion, etc. However, even in these like really, really small differences here, it might still be significant, and we won't really know until we push this data that was created through the Gravitational Wave Detection Program, which is called Enterprise. And that's the next step for us. And after that, we would similarly like to repeat this whole process again, except move the observatory in a different direction, because right now we're only moving in one direction. So yeah, that's what we've been working on. I would like to thank Haley Wall, Dr. Joe Glazer, Dr. Maura McLaughlin, and Will Fior for their guidance with this project, and also thank you for your time.